This webinar is dedicated to monitoring reservoir fluid movement during the energy transition for geothermal, CCUS, lithium explorations, and EOR++. So the controlled source electromagnetics method is a valuable tool for understanding reservoir fluids and their distribution. It's applicable in CO2 storage, enhanced oil recovery, geothermal exploration, and lithium exploration. And CSEM can be customized for specific reservoir goals by selecting the right components of the multi-component system. And with the interest of time, would like to present Kurt Struck to give us to run us through this webinar. Kurt is the president of Energy Transition International and KMS Technologies, KJT Enterprises, a pioneering company specializing in integrated seismic and electromagnetic technologies for the energy transition. His expertise spans various aspects of the energy transition, including CO2 monitoring, geothermal exploration, enhanced oil recovery, and the integration of electromagnetic solutions to reduce carbon footprints. With this, would like to give the word to Kurt and to take us through the webinar. And thanks to Lori and to SCG to organize this webinar. Kurt, please go ahead.
Good morning, everyone. And I have made an outline for 45 minutes, and I will try to stay below that. First, I'd like to explain to you the background of what fluid imaging is and why we're using electromagnetics, in particular controlled source electromagnetics. And then I will give you some examples for geothermal, CO2 monitoring, EOR, and lithium brine exploration. There's no question that climate change requires the reduction of greenhouse gases, and CO2 is one of them. So everything that we are doing is geared towards reducing the CO2. So the entire energy transition is trying to bring us to zero footprint. And note, it's a transition. It doesn't mean we get rid of the oil industry. It simply means that we have to get the oil industry to zero footprint. To give you an idea about the markets, of course, we as scientists expected this, but it is finally happening that the geothermal market is going to be 80 billion by 2030. And the last Geothermal Rising meeting showed it to everyone. It was extremely vibrant and busy, and it was good. There's a totally new industry. Of course, since we are geophysicists or scientists listening to this, we realize that a lot of the people don't really know yet what's going on, but that makes it so exciting for us. The CO2 market, which is very important, the CO2 market being the CO2 injection market, will only be 10 billion by year 2030. And the reason lies in having to fulfill all of the legal requirements and be compliant from an environmental point. And we need to store CO2 safe. That means we don't want to get it back, and we don't want to induce seismicity, and et cetera, et cetera. So we have to do a lot of geophysics to do this correctly. The enhanced oil recovery, or better said, enhanced oil recovery plus, that means we use CO2 injection to drive the oil out, can easily reduce the CO2 footprint when geophysics is used by 30 to 50%, almost within a short period of time. So this market is also very important to reduce the footprint, but also you can then capture the CO2 as you produce the oil. And we are doing this and replacing it with battery-driven machinery. And for battery-driven machinery, we need rare minerals or critical minerals, in particular lithium. And the first time I saw a lithium deposit was 1982. That resulted in me taking our magnetotelluric systems out of commission and trying to repair and calibrate them for a period of 2 years, because I couldn't believe that you could read this low conductivities. And now this is well accepted, and I will showcase histories for all of this. So what is fluid imaging? Let's first look at that a reservoir rock, and this is a picture of a clastic reservoir rock. A clastic means sedimentary, and we have here in orange the grains, and the fluid in the pore space, which is the space between the grains, is filled with water. We also can fill this with oil, and when we fill it with oil, we still have the grains water wet, unless we are producing too fast and are damaging the reservoir. I'm just throwing these terms in an explanatory fashion, so when you as geoscientists hear this, that you understand what reservoir engineers are talking about. So how do we measure this? We measure that in most cases from the borehole. That's not optimum, because the borehole only covers 10 to the minus 13 of a reservoir volume of 1 kilometer cube. And what we routinely try to do is we try to measure from the surface and calibrate against the borehole. Well, that calibration is really, really important. And you'll be pleased to hear that today is the first time I show how we can certify the measurements from day one by calibrating against the borehole measurements. Now here is an example of an oil reservoir, and every hydrocarbon reservoir, because hydrocarbons are lighter than water, has a brine below. So I'm showing this because this links really to the CO2 monitoring. And the oil reservoir is very resistive, and this is the oil reservoir. And this is the water above and the water below. And we preferably inject CO2 into the brine part of the reservoir, because brine, which is water saturated with salt, saline water of high salinity. It's important it's of high salinity, because everything changes when it's of low salinity. Allows up to 66% CO2 dissolved in the brine. And that is quite important. That means we can inject a large number of CO2 in the brine without really damaging the fluid balance. If we increase the CO2 saturation above that, we end up with pockets and pressures and problems. So monitoring it is extremely important to maintain the integrity of the reservoir. We'll get back to that when we talk about the CO2. Now, the methods that are used to monitor these fluids mostly electrical methods. Seismic methods are not that suitable for fluid monitoring, because seismic waves travel through the matrix, the solid part, predominantly, and electrical current is conducted through the water molecules in the fluid. If it's water saturated, there's more current flowing, fully water saturated. If it's oil saturated, the water content inside the oil will conduct it. Now, there are several techniques, and I use these names so that you have them when people talk about it. ERT, which is known as electrical resistivity tomography, is most commonly tested. It has very low resolution, it's depth limited, and it's highly inaccurate, but it works. I wouldn't say it works scientifically well. From an imaging viewpoint, you see something. It's a DC resistivity method. That means that the entire volume of investigation is between the current injection and the voltage electrode, so you have little to no volume focusing. Magnetotellurics, which takes the ratio between electric and magnetic fields, is better for larger depths, has very low coupling to resistors. It mostly looks at conductors, and because of that is limited. It's also limited because of the relatively low sensitivity. Controlled source electromagnetics could be the same as magnetotellurics. Some people call that CSEMT, but you do it controlled source EM to get a higher resolution. That means you bring your own transmitter, you do not take the ratio between the components, and you interpret each component independently, which you can do because you know where your signal comes from. So you get a better coupling, you can do good cross-calibration with logs, you get a better signal, and when you use a controlled source, a grounded dipole, you can resolve resistors as well as conductors. In fact, this is the reason of the growth of the entire marine CSEM industry, that controlled source electromagnetics can resolve resistors, hydrocarbons, which is also important for CO2. But I also will show you an example where controlled source electromagnetics resolves conductors. So it resolves both equally well. There are other methods. They are minor variation, and they just look at sweet spots. They're just mapping anomalies. And it's very important when you are in a drilling scenario where you actually spend a lot of money, that you know the reliability and the risk in order to mitigate excessive cost. Here's an example for EIT. Essentially, you have a transmitter in a borehole and receiver in another borehole, and you're making a straight line between transmitter and receiver. You move the receivers up and get more measurements. You move the transmitter down, move up and down, and you end up with this grid. And each of the measurements gives you R equals voltage over the current that you inject, gives you a resistivity. You average the resistivity from all of these measurements, and you get an approximate image like described here. And that's why it is simple, it's commonly used, and that's why it's a poor resolution and only approximate. Magnetotellurics gives you a good picture of the subsurface, and as I said, it mostly sees resistors. And when you do controlled source electromagnetics, the same picture gets a little bit better unblurred. So you can say the improved resolution is about a factor of 10, just to pull a number out of the top of my head. So those are the three principal methods. The first example I give you is for hydrothermal. And hydrothermal is when you are looking for hot water, mostly for hot springs and greenhouse heating and things like this. So a long time ago, we carried out a survey in the entire country of Hungary, where geothermal licenses were available. And we defined in that about 42 drill targets. And I'm reporting about the first one that was drilled here only. Obviously, after that success, things became commercially political in Hungary. And the clients have contacted us 3 or 4 times in the last 10 years, wanted to restart something, but nothing has happened thus far. So we carried out magnetotellurics, gravity, and we integrated seismic, gravity, and magnetotellurics. I will only talk about the integration part here. You will find on our website plenty of publications on what was actually done here. The well was successfully drilled, and we were off by about 30 meters at 1,500 meter steps approximately. And the well produced 4 megawatts of geothermal power from day one. Here is how we did this. The most important part in this application was actually the Hungarian geologist who took the old seismic, this is deep seismic data, and came up with a geologic model. And this is the well that was drilled based on our results. And looking essentially into an area with increased heat. And what that means, I will show you in the next diagrams. And this essentially gave the starting model. And with this starting model, the interpretation started. So we modeled the gravity and the magnetotelluric data, which we acquired. And you can see the MT sites labeled here. And I believe these are the gravity sites. And we found an area where we had a low resistivity anomaly. Low resistivity means we have increased water content in the rock, assuming the porosity is approximately the same, increased temperature, and low density anomaly in the gravity. The gravity data was inverted and the MT data was inverted. Both were inverted very similar by looking at residual components, and it was done in a cooperative fashion. And then these anomalies where the low resistivity and low density coincided That meant low density means more water, and low resistivity means higher temperature. That made an anomaly. We then mapped those anomalies back with the seismic, where we saw fracture zones, and then high-graded those anomalies where we had these two low resistivity, low density, and fracture zones into potential targets. Then before the drilling was done, after we had long done the report, the 3D models were rerun several times, and then during the drilling, they went after this particular anomaly. And this is then when they found 4 megawatts. Another case history is from Saudi Arabia. Ain al-Hara hot springs is along the Red Sea. And we work together with the KFUPM, which is located right here. And they have a controlled source EM system. And as part of the testing and the support, we helped them carrying out this geothermal work, which is still ongoing. And the surface temperature of the hot water is 96 degrees. There's not that many people yet, but they're planning to develop that area as a geothermal area. Now, magnetotellurics works like getting the electromagnetic fields from the ionosphere, which is the magnetic field, or from the meteorological layer, which are here, lights, Arctic lights, and the high frequencies get absorbed near surface and the low frequencies go deeper. And when we have a low resistivity heat zone, when you heat up rock, the resistivity goes down. Then you can see this. So magnetotellurics often sees the deep source rock. And then if you get high enough resolution and you can beat the noise, you see the heat sweet spot accumulations above. You lay out a number of receivers. You take the ratio of electric over magnetic field and you get an apparent resistivity. And these are tensor measurements because you lay out 5 components. And you can interpret it in 1, 2, and 3 dimensions. Now, in Saudi Arabia, because of the rough topography, and it's really rough topography, we also used other methods for static corrections. This is the layout, the magnetic field sensors, the electric field sensors, and the acquisition system. And we laid out a time domain system, a loop, 40 meters on the side with 10 meters in the center, and used those results for static corrections because the near surface effects of the electric field measurements can give you static distortions. And that was required in all of the measurements in Saudi Arabia. And you can see that here. This is a valley, and this is almost inaccessible. You can maybe use donkeys or carry the equipment up here. So people always ask, why are you taking lines directly along the valley? So somebody took, the PhD student took a cross line here, which is just another valley. But these sites are very, very difficult to access. So this has taken a long time to get these sites. And several years of studies, first geology, and there's lots of gravity data and seismic data. And so this profile from the west to the east, which you see here, is essentially seeing the hot spring. The hot spring is right there. There is a hot spring. From the west, yes, the hot spring is right here. You'll see a better picture in a second. And then the 3D inversion looks pretty much like this, where you have here the hot spring and you have local flow cells. And you'll understand by looking at the next picture why in the future we will be applying controlled source EM there to better understand this, because these flow cells that are postulated in here are very local and relatively shallow, and they can significantly change where you drill and how much geothermal energy you actually get out of this. And at the bottom, you may have the heat sources, but the heat needs to come up there through a certain fracture network. So here is the profile from the south on the left to the north west, and that is shown here. And again, you have the hot spring right here, and you can clearly see the fluid cell that you couldn't see in the 3D, the convection cell. And alone from this picture, you would say it would be a better location to drill here. And there is a plan to drill there and make a project which includes the drilling and controlled source EM. But you know, it takes time to get all that funding in place. Now, the geologic interpretation was actually done 1 year before the field work, and the geologic interpretation already postulated this. And so all of these models thus far are very consistent. And so we are quite excited when that funding comes to continue that work beyond just the MT measurements done by PhD students. So in geothermal, EM is a standard method for geothermal exploration. It allows you detailed targeting, and resistive zones require CSEM. And you have resistive zones that have increased geothermal heat capacity in places like Iceland and basaltic rock, where you have chemical alterations making that resistive. There are many case histories in public domain. The future is to have better borehole tools, because existing borehole tools do not go to high temperature. The borehole tools pretty much stop at 150 degrees C, and maybe 8, maybe 10 hours. Of course, the service companies claim longer, but the logging is very limited in hot wells. The next example is addressing a carbon dioxide sequestration. That means that we are taking the CO2 out of the atmosphere. We are capturing it when we produce hydrocarbons or wherever we capture it. And we are pumping it into the ground. And in the ground, it gets sequestered. And of course, hydrocarbon reservoirs are ideal to seal a CO2 storage reservoir because the seal is there, and then the CO2 doesn't come back. Now, another future area is to inject CO2 in basalt, because it is solidifying in basalt and thus will never escape, or also in crystalline rock, but that's not as common as the brine reservoirs. So what you do a baseline measurements. And in the baseline measurements, you get the background, and you get a background measurements. Here is displayed an apparent resistivity. And then you inject CO2. And after 2 years, the measured value in this case goes down. And after 5 years, you see yet another anomaly, which is the incremental part. And so mapping these anomalies is very important. Now, you can imagine, since the carbon credit business requires certification by the EPA or other government agencies, monitoring has to be very accurate and verifiable. So when we carried out the first test, one of the objectives was to deliver transparent data. That means that anybody can calculate the voltages that we have measured and verify that those are correct. That's number one. And number two, we tried to establish a correlation to the borehole. And I'll say a few words about that in the following slides. So what is happening is, and when you inject CO2, there are two issues with CO2. And the first issue is what happens to the reservoir fluid. When you inject CO2, the CO2 combines with the brine, with water molecules, and makes carbonates, and they become neutrally charged. So these are neutrally charged. They're bigger molecules than neutrally charged. We all remember that water is a dipole and has 3 electrons, and it's either positive or negative. So when you have a normal brine reservoir and it's mobile, you produce, these molecules move and the resistivity goes down. Any enhanced oil recovery, whether it's acoustic or electrical or force, reduces the resistivity of the reservoir significantly, because you are increasing the mobility of the water-saturated fluid part. And so in this case, when you inject CO2, you are increasing the resistivity. So a CO2 injected reservoir has an increased resistivity. not a decreased resistivity. So we are trying to map a resistor, but we are also trying to map where the water is. We are also trying to map a conductor. A second problem in CO2 is the seal break. And the reservoir seal is defined as the grain-to-grain contact between two different lithologies. The reservoir is in this case below. And when you push fluid through the reservoir, this seal, this grain-to-grain contact can break because of the stresses and strains you are exercising onto the grain-to-grain boundary. And every time you exercise anything on the grain, you are also exercising those same stresses on the pore fluids, which are right in between. So when it cracks and it breaks, you get a microseismic signal. And I'm also postulating, and we have observed that everywhere, we get usually also an electromagnetic signal before we see a microseismic signal. So when there is an earthquake, in most cases, we see an electromagnetic signal just before the earthquake, because you get that signal from the same forces acting on the pore volume. Now, monitoring usually requires a 3D modeling feasibility, and we go to the field and measure the local noise, add the noise to it, and optimize our sensor design and our spacing. And then when we carry out the survey to make sure that we maintain the quality of the data and the transparency, we carry out the quality assurance and support that with 3D modeling, so that we then control the acquisition process by feeding back overnight to the field crew whether they need to move the equipment or whether it needs to stay a little bit longer to get better data. The processing and evaluation is done very carefully, because the error needs to stay less than 0.5%, and this is 0.5% between the beginning and between the end of the survey. And again, this is supported by 3D modeling. And then before you do a repeat survey, you address those weak areas and you optimize the acquisition for a time lapse. Once you start monitoring, generally, let's assume a 10-year life cycle of a CO2 reservoir, then this monitoring will go on for 10 years, and you do not want to have too many changes in those 10 years. So that's why this predictive optimization is important. You saw this. I'll go back again and start it again. So now we are injecting a current, and the current which goes from here to here is perpendicular to these current density lines and goes downwards and outwards with increasing time. So we inject the square wave current through a transmitter. We lay out a bunch of receivers. In practice, we use the same magnetotelluric system that we use overnight to record magnetotellurics, and during the day we do controlled-source EM. But in this case, because of the low temperatures, that was minus 25 degrees C, we actually had a 24-hour operation, simply because I was really scared to turn off this 200 kilowatt generator in the evening and then turn it on in the morning again after it sat there for 10 hours at minus 25 degrees C. And these are the receivers and some pictures from the field. And you can also put shallow borehole tools down, which go up to 100 meters to measure that component. There are some advantages to that. Now, in North Dakota, we used 4 transmitters at 2 locations, both cross dipoles. We used those directions in order to see anisotropy and structure in the data. The injection site is near a power plant. There's a big power plant here. A lot of this is a lignite mine, and they need to have the carbon credits and inject the CO2, or they need to shut down the lignite mine. So it's very important for them to develop this. There is a potential site back here, but there also are some wells here. So this is why we made 2 lines like this and connected them. Whereas the reflection seismic covered the whole area as a grid, and they spent tens of millions of dollars on it. And this cost, this whole survey, including interpretation, cost about $900,000. So just to give you a factor of at least 35 to 40 cost difference. Now, these are the composite resistivity logs from several wells along here. And we built an anisotropic model out of it, which has 31 layers. The vertical resistivity is in pink, in blue is the horizontal resistivity. And these are not obtained by averaging. We are using the total conductance for the horizontal resistivity and the cumulative transverse resistance for the vertical resistivity. And we verify with 3D modeling that the equivalent 31 layer model is within 1% of the individual data points. The reason why we do that is because using all of the individual layers would become prohibitively expensive in computation time. Even for this small survey, the 3D modeling feasibility takes at least 2 to 4 months. We then have a 3D anisotropic borehole log, which we can then use to verify everything against. The horizontal blue lines are the seismic horizons, and we honor those when we average this. So in addition to the sensitivity-based averaging, we are also honoring the seismic horizons so that we can maintain that reservoir. In North Dakota, the two injection targets are at 1.6 kilometers and 3 kilometers. The deeper one is at 3 kilometers. The resistivity values are displayed here. Again, some equipment shots, but we did magnetotellurics for the background resistivity and CSEM. The magnetotellurics, we did 42 stations every 600 meters. The feasibility told us we needed 200-meter spacing for the CSEM, so we had 124 stations at each station, 5 components. So times 4 sources for each of the stations, so it's 4 times 5, 20 times 125, so easy 2.5. We ended up with different transmitter waveforms with 3,500 independent soundings and inversions, which told us that we had to have a different way of interpreting the data, which was totally data-driven and automated instead of driven by the brain of a single geophysicist. Here is the results for the magnetotellurics. On the left side, you see a single site processing. These are the quality assurance one. That means these are the 1D inversions. As reference, we have the horizontal part of the 3D anisotropic borehole log here, and you can see it matches nicely, but we do have a mismatch between the inversion result response in the solid line and the data here. So we applied a remote reference processing. We had 2 remote reference sites, one in 300 miles away north of it in Grand Forks, and one in Austin, Texas, a few thousand miles away. Both gave the same results. And you can see when you do remote reference processing, this anomaly is gone, which is lower frequency noise, and the match between the log and the inversion is even better. So we were very confident that this data was good. We then did the 3D inversion of these 2 lines. Here's the cross line, and you can see some deeper structures, but this is mostly to get the background. And the data gets shipped directly from the receiver to the cloud. We move this a little bit away to get it away from the analog parts to ship the data without any interference via the cell phone network. The Controlled-Source EM, which gives you more accuracy, this is only 1,200 meters of profile section on, I believe this is line 1. And you can see here the injection reservoirs, and this is the seismic, and it matches the seismic. All of the parts of the sections that we tried matches. Notice there's a mismatch here. This is because these are unsupervised inversion. That means there's no human interaction. The inversion starts with a half space and runs totally automatic, only using the data weights to influence the inversion. And they gave very consistent results. We tested that we had the sensitivity at depths. I skipped that in the interest of time here. So here we compare the 2D MT inversion of the same section with the section I just showed before. This is just a little bit lower resolution. But you can see here, if this is the MT with 2 sites and this is the CSEM, it gives you more detail in this area. We then included the seismic horizons into the 3D model and calculated for each side the response. And the dashed line is the response, in this case, for the electric field EX, EY, and the vertical magnetic field dB dt, dBz dt. And this is the reservoir response. So we are only interested in this part. And we can see that all of these components match the field data from the 3D response, which is quite impressive. The X field gets noisy earlier because it's lower, about half the amplitude of the Y field. That is related to the symmetry because the X field is in the same direction as the transmitter dipole. So if you use an east-west dipole, the X field is the east-west one. If you use a north-south one, the X field is a north-south one. And we see this consistently throughout the survey. And so we feel very comfortable that everything matches. And we feel like we can now say that the data itself is certified by the 3D anisotropic log, which is the ground truth. Obviously, being a geophysical measurement, if the log gets improved and changes, we have to go through this process and see within what confidence we can match then the change situation. So I have essentially given you the summary before I came to this slide. So the future for CO2 monitoring is to deal with the noise near the injection site, because obviously the injection hardware will generate a lot of electromagnetic noise. And we need to be more accurate with the focal point of the imaging, just like migration does in seismic. And that's why we measure multiple electric fields. And we actually have already the data to do this. We just haven't done that part of the imaging. The next example is for a water flood, and we are mapping a conductive anomaly. And I picked this because it's a conductive anomaly. And we did the same process as in North Dakota. We did a 3D feasibility. We did noise measurements. Here, we actually took an MT system to the side, and we measured MT, and we determined that the geology was layered. Beautiful site. We started out thinking that there's no possibility to find a site. Then we found a site. We found a well, we found a reservoir. We built the equipment custom built for this purpose. And then the objective is to see the water flood. This is a generic layout. In the field, there was only one line because there was only one test line done. And you have an injection well here, and these are producing wells, and you lay out a bunch of receivers across the flood front. And you're hoping to see this flood front because it allows you to optimize your production. You essentially can shut down your injectors before the water breaks through at the producing wells. Once the water breaks through at a producing well, it costs you $500,000 to work over that well and complete it again. So you do not want the water to break through at any production well. You want to know where the waterfront is. We also recorded seismic data here. We didn't interpret it, and I just show you the results for the magnetic field. Processing is standard. We did the typical digital signal processing, pre-stack, post-stack. A lot of filtering done because the data was very noisy because it was an experiment. And then a lot of interpretation done to get to the results I'm about to show you. Here's some data. This is the current. These are the electric fields. This is the magnetic field. After signal averaging or stacking, the electric field looks like this and the magnetic field like that. The transmitter was in this direction. The water flood was here. The water was injected in 2-kilometer steps from a horizontal well that was drilled from about 4 kilometers away. So there was no well directly nearby. This is the center receiver, and this is the 400-meter away receiver at the edge of the line. These are the 3D modeling results, and these are the actual measurements. So where the water was injected, we got after 2 days an anomaly of 30%. And this is the reservoir changes as we predicted them. The reservoir changes are between 0.1 seconds and 1 second. And 400 meters away, I would not say, when I look at the data, that this is an anomaly because it's noisy and only 2%. But knowing where the reservoir is, we probably still see something. And the 3D modeling sees in both cases a much stronger anomaly. And we had no explanation for that. We now understand it because we compared notes with other companies doing similar things, multinational oil companies. And they say it's the casing, and we say, no, it's not the casing. We modeled all the casing. There are dozens of casings nearby. And the casing doesn't give you the anomaly enhancement. So what we think it is that this current gets channeled into the water flood. And since they're pumping 8,000 liters of water, I think every hour into the ground, it's a large amount of water. And so the electrical current is essentially channeling in here, which gives you an anomaly enhancement, which is the only explanation that we can find. And that seems to be making sense. The result is that CSEM clearly sees a conductive anomaly. In this case, we have to add borehole measurements and build the linkage. Next, we will address lithium brine. In Nevada, EM is standard, in particular in the Railroad Valley. That's the place where I looked for geothermal in 1982 and 81, 82. And we stopped and thought our equipment was not working because we could not imagine to find a 0.30 meter conductor at 1 kilometer depth. That's ocean, seawater. There is no ocean at 1 kilometer depth. In Sweden, where they are now moving villages to mine the lithium, electromagnetics is a standard tool. Argentina, part of the Golden Triangle, Chile, Argentina, Brazil, electromagnetics is extremely successful and they're mining it. And in Saudi Arabia, we did several tests with our client. We are postulating that there is a deposit and hopefully that will be followed up and eventually drilled. So what's happening with lithium brine? You need a salar, which is nothing else than a dry sea, like the Salton Sea in the Imperial Valley or the Dead Sea in Israel. And what you also need mountains. You need the minerals from the mountains. If you don't have the minerals from the mountains, you do not have the mineral well, it's not a condensation kernel, but we all know that rain only happens with the aerosols in the air. That means you have to have dust in the air where the water can collect. So here you need to have minerals where the water can evaporate and the electric charges can collect. And these minerals must be the right type of minerals that they can actually hold electric charges. And lithium is one of those minerals. And so when you have this coming from the mountain range, then you are essentially accumulating in lithium brine, and this lithium brine can then be used to build batteries. And you can see here, Chile, Argentina, and Brazil are part of the Golden Triangle. China has large lithium, Australia, the US is right here. And now you have Portugal, but Sweden is also coming up there very fast. There are two examples I'll show you done by a colleague of us. She's also co-author on the paper that I'll give you the citation at the end. And they're both from Argentina, the first example. And what we can see here is that the low resistivity is blue, and you can see strong low resistivity layers, and you have about 3,300 meters. You have them 3,500 meters. So you have them at about 400 meters. And you have essentially these are the lithium brines. And the same here. This is another example, all drilled, and they're very successful. They keep going. Here again is the lithium brine. This is about 400 meter steps. And you have some other low resistivity anomaly right here. Then this is more resistive, and then this would be the lithium brine. Now in Saudi Arabia, if you remember the map from Saudi Arabia, we have a test site near Daman and a Half Moon area, and then we have another test site near Riyadh. And in both cases, we see very similar results. We have MT measurements, and the MT measurements see a conductor of 0.2, 0.3, between 0.3 and 0.4 ohmmeters at approximately 2, 3, 4, 500 meter steps. And these are the CSEM response from the same side. And you have the two different CSEM models. Somehow the MT model is not displayed on this. This is my mistake. But you see also in the CSEM model, you see a very strong conductor right here, which is approximately the same depth. And so this is the MT model. These colors are wrong. So this one is the MT model, and this one is the CSEM model. It's just a flip on the color scale. And you see a similar low conductor, not quite as low as in the MT, but you see this conductor essentially matches, and the conductor has to go more down than it is here. So lithium deposits are extremely conductive. The hardware requires extended dynamic range. We are applying tricks in our amplifiers that we use for controlled source EM, and they give us also the advantage of being able to deal with larger dynamic range in magnetotelluric signals, which is the reason for the performance. And in the future, the system has to be made for better use in hostile environment, because most of these lithium environments are really unpleasant, hostile deserts where it's almost impossible to drill holes. So we'll have to address a lot of these operational issues to be able to record the data more efficiently. And last but not least, I'll invite you to look at the recently published paper, which summarizes all of this. And Cesar, my co-author of this presentation, is the senior author there. Anna did the lithium, and Pantelis did the lithium in Saudi Arabia and the geothermal. Yardinia did the interpretation, and Anvi did the acquisition for North Dakota, both MT and CSEM. So all of the guys are on here. And with that, I'll open the floor for any questions.
Thank you, Kurt. Thank you for a very informative webinar. We have several questions in the Q&A box. But first, if people asking could raise their hands and we could unmute them, so you can ask directly. Jin Lee, would you like to raise your hand and ask your question live?
Thank you very much. It's a great talk. I'm a geophysicist on the seismic side, not the EM side, so I'm kind of new. But I know I knew that the CSEM is great for the hydrocarbon detection, and it is now available for the CCUS monitoring. I have one question about the one of the documents published in UK, which is for the endurance CCS project. It listed a lot of M&B monitoring and verification, which is CCS monitoring. It tests a lot of technologies is listed. One of them is CCM, the CSEM, but it has marked as red. It is not not appropriate for the endurance field. So I don't know why, because my understanding is it's a great tool for detecting the CO2. So do you have some ideas about the background of the documentation?
I'm trying to understand the question that you had. There's something in the UK and they didn't think CSEM was the right tool to apply.
Yeah, it is T-side CCS project.
Yeah, but we can do that by email. In most cases, the evaluation of CSEM is done amateurish by either using the wrong method or the wrong application. So everything that you see published about Northern Light, great examples, but 20, 30 years time lapse. That's not very practical. So we are looking at time lapse in North Dakota, repeat measurements, and the plume having moved by 200 meters after 18 months. So it needs to be something practical. So you have to fine tune the method and understand the method within the context of practical application. That's why the feasibility is so important. If you choose some wide targets, and I've seen some gravity examples where people are talking about 50, hundreds of years of changes, Why are we talking about that? Because we will all be dead, and it needs to be practical. So you have to give me the details, and then I will answer your question. There are a lot of cases where CSEM may not work. We are not saying that it works everywhere. In fact, we always say that you have to do a 3D feasibility before you do any data acquisition. But we do know when people don't do a 3D feasibility, they hardly ever get reliable results.
All right, thank you.
Thank you.
I will answer every email in 24 hours, or at least I will tell you I'm busy, I will answer later. So if I don't respond in 24 hours, send it again, then it got lost. I get a lot of emails.
Thank you, Jin. Thank you, Kurt. We go to the next. So let's go to Jim De Siena. You have raised your hand. I will unmute.
Hey, Kurt. Jim De Siena here.
Well, I'm happy to see you.
Hey, could you comment more on CO2 leakage beyond the the microseismic fracturing of the seal? What about fault dilatancy and CO2 seepage? Would you detect that with CSEM? And then a follow-up to that relates to this CO2 is going to leak into some thief zone. So kind of put that in perspective as well.
So the second question I didn't quite get because I was talking. So let me ask the first question. Seepage is going to be a small leakage, and my feeling is that's going to be small volumes. It's all a matter of volume effect and conductivity. I do not know. This is why I'm postulating to go more into the borehole, and we have a design for borehole sensors. Once you are in the borehole, and similar to DAS, you have much more opportunities to detect that. From the surface, a seepage, not a leak. You won't get me to tell you that you can detect that. Let's put it that way. And the 0.5% accuracy, we are referring to repeatability, including instrument accuracy, sensor accuracy, location accuracy, blah, 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 over 2 months. So that's where our error estimate comes from. A lot of that is operational. And so within that error, you're trying to find a seepage very low down. I would not even recommend to do 3D modeling for that. Now, what I can tell you what we are trying to do, and I don't know if my colleague Andri in Indonesia is on this call, but I'm trying to get him to show with some 3D models that we are actually seeing a conductive anomaly at the flood front as the resistive front is sweeping through the reservoir. We have seen in some 3D models a conductive anomaly. If we can show that clearly in 3D models, I can guarantee you we will improve the measurement accuracy to be able to see that. But that is a sweeping front, which is a larger anomaly than a seepage. So, but first, I'm honored that you're coming to this webinar.
Well, no, I mean, I always got to keep asking questions, so that's how we all learn. But yeah, I like your idea of the conductive front, because we do know that the CO2 is going to push a bank of the brine ahead of itself, and that might even move into a lower salinity area, so you can see that. But what about I know you can monitor if we have a thief zone in a shallow section, and that fault linkage got into a thief zone, we'd see that as a shallow anomaly. But can you detect it if it gets into the aquifer, which is a fresh aquifer? And I'm adding CO2 to a fresh aquifer.
Hang on, Jim. First of all, for everybody's benefits, a thief zone is inside a reservoir, a zone of higher permeability, which allows the fluids to swoosh away to another compartment in the reservoir. So if you have a CO2 thief zone, that means you have a larger amount of fluids moving around. We have in our system right now, through measurement focusing and through hardware focusing and noise cancellation, we can at least improve the sensitivity by a factor of 100, 2 orders of magnitude. We've proven that over the last 30 years with the technique. We just haven't implemented the techniques because of lack of projects and funding and so forth. So we know we can do that. So if you would go after thief zones, the existing measurement philosophy and data would be sufficient to detect the sieve zones, because the anomalies would be large enough and the contrast would be large enough. A sieve zone with a resistive fluid will stick out like a sore thumb in the electric fields, as long as you can focus the electric field in volume. So focusing of the electric fields is mandatory to find your sieve zone.
No, thanks. That answers my question, and great presentation. I got to drop off.
You can have
Thank you,
it, Jim. I'm going to make this available to people that want to use it.
Thank you. Next, we go to Berthold. I will unmute.
Very nice portfolio of the EM application, linking it as well to the geology. That was very nice, very nice. This is a minor question that I had. On one of your examples, you were calculating the transverse resistance to get RV and the horizontal conductance to get RH. And this calculation yielded an RV over RH ratio more than 10. I think that should have raised a red flag, because when we measured RV and RH using borehole 3D borehole logging tools, we never saw this ratio. I mean, I think that ratio more than 10.
Better. First of all, we are using the anisotropy coefficient, which is the square root of the values that you were using in the logging world, because there you use the ratio as you just explained it. First of all, thanks for your flowers and thanks for joining. We do not see an anisotropy coefficient higher than 10. They're all between 1 and 3 or something like this. There is another part of the presentation, and in the paper, we are actually plotting the coefficient of anisotropy, because we also invert for it, because it tells you about the focusing with depths and things like this. So I'll have to look at that. But I did not see anything anomalous in the anisotropy coefficient. And in both cases, we are using the cumulative conductance and the cumulative transverse resistance, except that in our terminology in geophysics, cumulative conductance is replaced by conductance. And there is not the same thing for transverse resistance. So that's why transverse resistance has the word cumulative in it.
Just to sum it up, but again, it's okay, because it was one of the exercises that you did there to calculate RV. And again, I think that should have raised the red flag word.
So I look at it as well, so that we don't. But my feeling is that they were all between 1 and 3. So and a maximum resistivity ratio of a 10 in this type of environment is not unusual. The Williston Basin is the most surprising basin for electrical geophysicists. I sat on a well log for 1 year before we looked at it. That was the Barken for frac monitoring. And then we realized we were able to see from the surface a 30-meter thick reservoir at 10,000 feet at 3.5 kilometer depth. I would have never imagined that. So in the Williston Basin, you have very large resistivity contrasts. Very favorable for electromagnetics. And North Dakota is in the Williston Basin. Anna had a question. Is Anna still?
Yes.
I saw her question. So Anna talked about the accuracy of the measurements, the degree for RV or RH. So there is absolutely no bias between the sensitivity of each of these sensors. All of our amplifiers are done the same. The magnetic field sensors are completely sealed. We do not ground our receivers, even though we can. So there is, in terms of accuracy, they are both identical. In terms of noise, the problem we have with the magnetic field sensors, that near the power plant, the future injection site, that the sensors go into saturation. And once the sensor goes into saturation, that component is dead. So the magnetic field sensors are a little bit more noisy because of the external noise. But we stack long enough that we can deal with it. For the next survey, we would stack the magnetic field longer. We stacked 4 hours in the North Dakota survey. We would probably go to 6 to 8 hours in order to improve that for time-lapse measurements, or build some secret new sensors, which we've already designed. So that should answer Anna's question.
Now we go to Job.
Somebody
Yes.
wants to know about the software for the 3D model. That's the Drushkin and Davidiceva software. We market that software. We call it CSEM emulator, also known as MaxAnis. It's used by most service companies, logging service companies, and many big oil companies have it as well. And the software has been under development for over 30, 40 years. And Drushkin and Davidiceva are still working on supporting it.
Okay.
So you can get the software from us. Universities get a special discount.
Okay, if I may use the opportunity to ask questions, is that right?
Yep, please go ahead.
Okay, good. Well, we met many years ago, and it's a pleasure to hear you again. I have a few simple questions. The first one is, which frequency ranges did you use for your CSEM?
Our systems are broadband, so our systems are wide open. Let me just pull up the slide, show you. So about the equivalent of 16 seconds would be the lowest frequency, and the highest frequency is 15, 20 hertz. So this would be 16 seconds from here to here. And the switching is 70, 80 millisecond constant, all the same. So you are 10 hertz, a little bit more, 15 hertz is the maximum frequency you have in the signal. And then you go as low as this down. We do not use any analog filters, so there is no low-cut filter in the system. That is absolutely essential in order to get the high accuracy. If you put a low-cut filter in, you're getting nothing. So the system is broadband, but from the design of the system, we are staying in this frequency window, which is essentially from 1 second to 2, 3, 4, 5, 6. So we are staying in that window, but you need the low end of the spectrum in order to get the reference DC level and the high accuracy of those signals.
Okay. Yeah, thanks. Then
So
the other
it's
question.
broadband, but our system can do any frequency you want. Essentially, we can acquire up to 80 kilohertz for each channel, and it goes all the way down to DC, literally DC. We use in some cases flux gate magnetometers that go down to 10 to the -7. You just have to record long enough.
Okay, the other question I have is, in Hungary, the inversion of the seismic and the gravity, was that done jointly or sequentially?
Cooperative. One guy would do the gravity inversion and the other guy would do the MT inversion, and they would look over each other's shoulder.
So it's not purely jointly then?
It's purely joint. This was done a number of years ago. In Hungary, it also makes sense. In particular, your former employer has been telling people that they prefer 3D modeling over 3D inversion. The final drilling model required many reruns of the 3D modeling, both the gravity as well as the MT, because the geology kept moving the model more than any software could do to get the final drilling location based on the geologic interpretation of this very old seismic. There were, by the way, also 5,000 old MT sites done in Hungary with some old systems that were not useful. They had absolutely no information above 5 kilometers. We experienced the same in Germany for a subsalt project, that the old MT sites in Germany were not useful. So the important part in Hungary is really to make the geology consistent and get all of the geoscientific data consistent. So a joint inversion would have given us as geophysicists a little bit better feeling, but we still would have had to run the 3D models for both the gravity and the MT when we had the final drilling location. The final model that was drilled is very different than the final model from our report. So there were many reinterpretations done by the geologist with us, guiding us afterwards.
Okay, thanks. The other one is, you measured the horizontal resistivity. Now, did you find any differences, say anisotropy in the X and Y directions?
In which case? In the one in Asia, I didn't show the model because the location is confidential, but we do have the anisotropy, and we do see the anisotropy. All of our models with CSEM include anisotropy. We do not calculate isotropic models because the error by ignoring anisotropy, and this is I had in my previous talks, is 30 to 50%. So I do not think isotropic models would get you the results that we have. In fact, I see it from our Chinese colleagues many times that they interpret induced polarization where it's really anisotropy. So MT doesn't see much anisotropy in sedimentary environments. So for MT, it's okay. But CSEM is very sensitive to anisotropy. So we do have that. We did not see much directional dependence between the different transmitter locations, the different directions, and the receiver locations in North Dakota. And there we have 2 north-south receivers and 2 east-west receivers. On one leg of one receiver on the south, and it was the east-west receiver, we saw some directional dependence at 500 meters depths. Now, normally you would say that's static shift, but 500 meters is not static shift, and it's not a pipeline either. So it's some paleo channel or something. But we did see some local anomaly, but in the final interpretation, that got smeared. In the data, we saw it when we did the quality assurance. So we were lucky that we could interpret the data without considering that. But otherwise, the data was extremely well behaved. In fact, in North Dakota, you probably could have lived with one transmitter, but for the same reason, I would never recommend one transmitter to exactly know the directional dependence. And in Asia, even the MT is one-dimensional. The oil field in Asia, which by the way is also a former shell oil field onshore, is beautiful. I mean, steel pipelines at the surface, and you have absolutely no noise from the pipelines. It's just absolutely beautiful. Very quiet, very well behaved.
Okay, then my last question is, do you see any use of machine learning in the area of EM?
Yes, we've published a paper on that 2 years ago. It's on our website. We do everything in the cloud, and we have already run prototypes for the quality assurance using artificial intelligence for the MT, because the 3D MT inversion we do within about a week after the survey. The CSEM still takes a lot longer. We are trying to substitute the excessive time it requires for the 3D modeling with machine learning. And you can see also on our websites that we have filed for patents for that. They're almost expired. That's how old they are. And so, yes, we do plan to integrate that so that we can essentially give the operators a cell phone, and they push a button, they push in a number, and they get back green or red, and they know they can pick up the receiver and go on.
Oh, excellent,
so
excellent.
we are planning to do that. So at the moment, we are trying to reduce the time. Well, I'll give you an idea. When we acquire 4 hours of data continuously, 6 channels at each side, 15 sites, each of them at 1 kilohertz sampling rate, you end up with a lot of data. This data needs to come through the internet. You end up with 20 to 30 files, separate files, that you have to splice together, which takes a long time. Make sure the headers are correct and everything else, and they get normalized, and or the garbage get cut out. All of this is subject to machine learning. Then you have to average all of these files. We only use 1 or 2 files in the quality assurance overnight. We can't do that with 30 files for each of these components. It's a really excessive time requirement that's impossible to handle. And it's not a matter of computer time. It's a matter of steps and workflows and automation.
Yeah.
And that's where artificial intelligence comes in. So if you look at the paper on our website about cloud application wizards, you will see that we are using also operator parameters in order to determine this, because we find those equally important as some mathematical equations for our electromagnetic fields.
Well, thanks very much, Kurt.
Thank you, Jep. And then we go to our next question from Olusegun. You're asking about use of these electromagnetics for to confirm the dynamic reservoir models, but maybe we can give more details on terms of what type of reservoirs you're looking for. You are unmuting you.
Okay, good afternoon. And can you guys hear me? Thanks so much for this wonderful presentation. It's really an eye-opener because I never knew the controlled source electromagnetic method could also solve this problem. I always think it's only through 4D seismic technology because I'm presently working on the 4D seismic, trying to validate the dynamic reservoir simulation model with 4D seismic in order to understand the fluid behavior over time. But I want to also know if this technology we discussed into this webinar could also solve this problem. I'm actually working on the siliciclastic reservoir within the Brazilian field. So that is my major question. Thank you.
In which field?
Campos Basin in Brazil, the Brazilian field.
Well, you know, Petrobras uses a lot controlled source EM, in particular in the Campos Basin. So, and they are actually building their own controlled source EM system for reservoir monitoring. It's the only company that found that's approved. So the value equation is there. To answer your question. But look, seismic is a fourth order effect of the fluid sensitivity. Seismic is the best geophysical technique and has very high resolution. And if seismic works very well, there's no reason to use controlled source EM. Let's be very clear. But in some areas where seismic doesn't work very well, there is no other choice. Now, distinguishing between oil and CO2 saturation or brine and CO2 saturation is very difficult for seismic. Working through basalts or salt domes is impossible. So there are many areas, carbonates, seismic doesn't work well, sweet spots in carbonates, in particular pre-salt in the Campos Basin. I mean,
yeah, salts.
And Petrobras is spending hundreds of thousands of dollars for close to $500,000 per good full waveform inversion in the Campos Basin. So, you know, you're never going to spend this much for CSEM, but the value could be very high. I have another presentation on multiphysics where the seismic pre-step depth migration or full waveform inversion is significantly improved if you constrain it with electromagnetics. So that is a huge saving and a huge improvement. Subsalt becomes much easier if you add electromagnetics to it. Electromagnetics does not have the resolution of seismic, but then seismic does not have the fluid sensitivity of electromagnetics. So you use essentially seismic to get the container outside and electromagnetics to find out whether you have black coffee or a cappuccino in your container.
Thank you. Thank you for the question, Olusegun. Let me see. Jean Lee.
Yeah, hi. Thank you for all the questions and great answers. By the way, you just mentioned about combining seismic and an EM. In most cases, for example, if you have a full waveform inversion with very fine-tuned velocity, is it going to be used as joint inversion for the EM, or how do you use that jointly?
I have to give you two answers to this because I have certain experience with this type of inversion, which is not favorable. So the market is very much going towards joint inversion. In fact, there is an increased request of using seismic to constrain the electromagnetic and vice versa. But these constraints are oversimplifying the model. We are putting too much geophysical brain into the results. You know, the geophysicist, when somebody says how much is 1 and 1, everybody comes up with certain answers, and the geophysicist says, what do you want it to be? So joint inversion is a good tool, don't get me wrong. And I have some evaluations on the different ways in my book. In fact, I was going to do that as my PhD and do exactly the constrained joint inversion with seismic. And Kiva Vozov, my PhD supervisor, looked at me and says, I'm not going to give you a PhD for that. That's not worth a PhD. And I looked at him and my mouth was wide open. And he was right.
We're losing you, Kurt, for a second. Can you please repeat?
And I said this, I was trying to do that as my PhD 40 years ago. And Kiva Vozov told me, you're not going to get a PhD from me for that. And my mouth was wide open. And 20 years later, I wrote this up in my book. Any type of constraints in the inversion are forcing the model. The beauty of the North Dakota data is there was no constraint on the data. There was actually no processing done. The data was just averaged and the weights used in the inversion. That's it. Model was all straight. So we need to get our acquisition and processing together that we can do this in time lapse. The biggest problem 4D seismic had is that when they redid 4D seismic, they couldn't match the previous results, different system, different processing. So I'm trying to avoid that mistake. So we are trying to modify and play hand in hand between data and inversion. So this is the critical side. Obviously, joint inversion could be a very good tool, and it can give you good results, and it can make 1 and 1 3, but you have to pay the price. And the price is you have to oversimplify the model, and the model comes from the geophysicist. And if the geophysicist and Mother Earth would ever talk together, Mother Earth would say, I don't understand it. The Earth is what the Earth is. So the data is what needs to tell us what the model is, not the geophysicist. And that's the strength of seismic. In seismic, you can image the data to the model. And in inversion, the model comes from the brains of the geophysicists. So, yes, we are all going there. The industry requires it. I have to tell my guys, we have to hurry up with our joint inversion, gravity, seismic, magnetotellurics to be able to have the cross conditioning and cross constraints and get all of these in one joint inversion because the customer wants it. But the practicality tells you that the data is where the truth is, not the inversion model.
But with repeated measurements over time, so when you do the 4D measurements, you can constrain, perhaps get more information and then optimize the constraints. By that, to get the inversion work better and better, because we get more information about it both from the 4D seismics.
Yes, it's a tool, but it's a tool for the interpreter. Yeah. And you have to clearly distinguish between our tools. And I mean, I use, if I hook up some 3-phase appliances or something, I use a voltmeter to measure the voltages to make sure that the outlet is wired correctly. The voltmeter is a tool. I could also use my finger.
I wouldn't be very...
In Europe, yeah. 220. In the US, 110 is nothing.
Right. Thank you, Kurt. Thank you, Jin Lee. Do you want... yeah.
Thank you.
Yeah, are there any more questions in the chat box? I don't see the questions in QA box or in the chat box. Are there any more questions from the attendees? Kurt, this is probably one of the high-end participations. I think we are over 50 participants, and it's almost 2 hours. So
yeah, we're at 115. Well, thank you very much to everybody. I'm really humbled and honored by you coming to this webinar. So
thank you, Kurt. Thank you, Kurt, and thank you, Laurie and Anthony and SCG for organizing this webinar. This webinar will be is recorded and will be available. Thank you. Thank you, Kurt.
Thank you. Bye-bye.
Thank you. Bye-bye.